Hello. Thanks for coming to this talk. There's a good competition out there, including one I would have loved to go to, Karen's. So the talk, the title is focused on RISC-V, but it's a bit broader than that. It's a lot what's going on in seL4 land. So who knows what seL4 is? Oh, wow, almost everyone, not just my students. That's very good, so I can skip over the marketing stuff quickly. So yeah, there was this 30-year dream of verifying operating systems. This is from 1980, where people first tried it and failed. And seL4 is basically the dream come true. So it is the first operating system with provable security enforcement. And when I say provable, is mathematical machine check proof. It's also the only, at least in the open literature, protected mode OS with a sound and complete worst-case execution time analysis. In other words, the only system on which you can, protected mode system on which you can do hard real-time in the presence of untrustworthy software. And we took that a bit further 2 years ago to support true mixed criticality systems, so you can ensure timeliness even if there's not trustworthy code on the system. And besides all that, it's the designed for real-world use, and in particular, it's the fastest of its class, despite all the verifications. So my motto is, security is no excuse for poor performance. And of course, it's open source, otherwise I wouldn't be here. Okay, so that's the end of the blatant marketing. There's a lot of history in this class of microkernels called the L4 microkernel family, which goes back to the early 90s. And everything in green is where I had my hand in, including the one that was shipping on Qualcomm modem chips starting now 12, 13 years ago, and the one that runs on all the iOS devices, so anyone who has an iPhone, iPad, whatever, that runs on the Secure Enclave is one of our earlier kernels. So seL4 was built on the background of this 20 years experience with high-performance microkernels. So given from them, almost everyone had their hand up, I assume that people generally understand what a microkernel is. So microkernel has no actual services. Anything you expect from an operating system is built on top in user level. So there is all your system services. They run as individual protected processes. You can also run virtual machines. So seL4 is not just a microkernel. It serves as a hypervisor. And we can run Linux on top. And the kernel's main job is to isolate these different processes from each other, but allow controlled communication. And controlled communication in a very strict sense, two units can only communicate if they've been explicitly authorized. And so the kernel in steady-state operation is just a fast context switch machine. And apps run either native or in a virtual machine. And the main mechanism that gives us this control is capabilities. Who knows what object capabilities are? Most people, they're not what Linux calls capability. The Linux folks have taken a well-defined term and abused it to something much less powerful. Object capabilities are safe references to objects that provide primary facial evidence of an access. And the system will let you do the access if and only if you present the right capability. So this gives you an object-oriented flavor to the system. A capability refers an object and encodes access rights. And the nice thing about capabilities, and the reason why every real security-conscious system is based on capabilities, is that it gives you very fine-grained access control, down to individual pages, etc. One implication of the microkernel approach has to do with licensing. So seL4 is licensed under GPL v2, exactly the same license conditions as the Linux kernel. We went out of our way to make sure it's an exact match, including providing the same clarifications, etc. But of course, that means the GPL is really only applies to the kernel, which is much less than in a Linux case. So all your typical system services, they can be under any license. They can be GPL, BSD, or closed source. And when, for example, the only reason why someone who wants to deploy seL4 would have to modify the GPL code is to do a platform port. And because in seL4 all device drivers are user-level programs, the kernel doesn't have device drivers, so except for a timer driver and a interrupt control driver. And for debugging, if it's configured for debugging, also a serial port. So basically, the stuff that you need to GPL when you do a platform port is just boring boilerplate. Anything that's really interesting IP-wise is your application code, which can be under any license, and whatever extra system service you need or modify, they can be under any licenses. In contrast, in Linux, if you do a platform port, you have the device drivers in the kernel, they have to be GPL'd. And if you modify any system services, etc., they have to be GPL'd as well. So in terms of IP effectiveness, the GPL implications are much less in the microkernel. We can argue whether that's a good thing or a bad thing. I actually think on balance it's a good thing. But obviously opinions will differ there, and I'm happy to have some offline discussion, and there's a discussion on the blog here. So one of the things, seL4 has been designed for security and with view of deploying it in security and safety critical systems from the beginning. And this is a few things it's been deployed on in the DARPA HACMS program. On the left, you see an autonomous helicopter. This is a standard helicopter airframe Boeing converted for autonomous flight that was flying on seL4, US Army trucks that drive autonomously. So these are real world systems, and they started off being incredibly unsecure. So the professional hackers took about 2 weeks to completely own that helicopter, which is interesting given this is supposed to be a military hardware. So easy to compromise. After re-engineering this thing, it was actually done by the Boeing engineers, we kept the hackers out. So that was really cool. And the effort of that was about 2 people over 2 years, which is tiny compared to the overall project cost. There's a few other things like the secure comms dongle, that has been certified for military use up to secret. This is pretty significant because that was the first time a military level government security certification authority has accepted software enforced isolation as equivalent to physical air gapping. It's a major step. And seL4 is the only system that can get this kind of approval. And there's other things. So the real core thing about seL4 is its verification story. And so this is the mathematical proofs. And what do I mean when I say verification? I'll start with ARMv7, which is the platform where we have the most comprehensive verification story and where we started it. Well, we started on v6, but v7 is almost the same. So we have the kernel, which is implemented in C, which is about 10,000 lines of C. The original version was about 9. It's now about 10. And then we have an abstract model, which is an operational description of the kernel's functionality in a mathematical logic. And then we have these machine-checked mathematical proofs, and there's lots of them, that show that under certain assumptions on the C semantics, this C code will behave only as allowed by the abstract spec. So in a very extremely strict sense, the implementation is bug-free, provably. And then there is this next step that shows that the binary is a correct translation on the C, which among others means obviously we take the compiler out of the trusted computing base, so we can use standard GCC, and we don't have to trust our assumptions on C semantics because they fall out by the complete proof chain. And then, okay, the abstract model may be crap. Well, we can prove that it's not by proving that it can enforce the security properties. And we've done all that. So we've got this complete proof chain from high-level security properties down to the binary that runs on the silicon, which means it's really awesomely bulletproof. And we have the sound worst-case execution time analysis. For truth in advertising, there is a few things that are not yet done, and they're all work in progress. So kernel initialization is not yet verified. In other words, we have to trust that the init code gets the kernel into a safe state, and then our proofs show it will remain in a safe state. Obviously, this is a poor assumption. You don't want to keep that, so we're working on fixing that. some privileged state, in particular address translation, is modeled a bit more high level at the moment. We're working on fixing that. And timing channels are not precluded because this formalism has no notion of time. But I'll show you later what we do on this space. Any questions up to this point? Yes?
What about hardware? Say you have a software that starts...
Well, if you have a bug in the hardware, you have a bug in the hardware. No operating system can protect you against that. This is an assumption everyone makes, whether you verify your operating system or not, right? If your hardware is broken, your system is broken. If you know about the hardware bugs, you may be able to work around them. If you don't know them, you have no chance, verification or not.
When you say MMU and caches are modeled abstractly, do you mean that the system is only provably secure if you disable the MMU and caches?
No, that is not. Well,
okay.
it is provably secure under the assumption that the things we axiomized, basically stated without proof, are correct. And you can validate these with code inspection and testing, which we do. But it's not the final state, right? We will fix that. Okay, so RISC-V. What are we doing with RISC-V? It's not RISC-V, by the way, it's RISC-V. So a little bit of background there. There's this company in Germany, in Munich, based HENSOLDT Cyber. I didn't disclose that I'm indirect shareholder of it. They are trying to build some really, really secure systems, including addressing the hardware. So what they're doing is they're building their own chip. And we should have the first samples of that within 2 months from now. And it's a RISC-V processor based on the open source Ariane RISC-V implementation from ETH. So ETH has produced this open source Ariane implementation of RISC-V, which is now basically the foundation block of the Open Hardware Foundation, if you heard of that. So they fed that in. And on top of that, they have a supply chain security story. Basically, they use an approach called design encryption or logic encryption to protect against Trojans being inserted into the processor during the production process in an untrusted fab. It's not 100% security against any attacks, but it addresses the biggest attack vector. So this is really cool stuff. So an actual secure processor doesn't mean it's provably correct. There could still be bugs in the processor, but at least it's a good protection against people trying to sneak a Trojan into you without you knowing. And then, obviously, that's why I'm involved. We combine that with a secure operating system based, not surprisingly, on seL4. So this is what they want to do, and they want to have their first product ready about mid-year this year. And so they needed, the whole thing only makes sense if seL4 is verified, so they needed verified seL4. So they actually, out of their pockets, with a bit persuasion by me, of course, decided to fund this RISC-V port of seL4. And we did it. The port has been running for a while. This is sort of performance comparison. So what we show here is round-trip IPC time. So this is the critical operation in the microkernel. You invoke a service and you get back. The turnaround time for invoking a null service in a different protection domain or in the same. 32-bit x86, 64-bit x86, and 32-bit and 64-bit ARM. The x86-bit are actually a bit cheating because we disable the spectre defenses. If we have the spectre defenses enabled, then the numbers are way bigger. But we basically do a best case performance, and this is our RISC-V implementation at the moment. There's still scope for optimization. We haven't invested as much in micro-optimizing the code as we did on others. And you can see, if you look at the top line, the intra-address space IPC cost, it's very comparable. It's a bit faster than ARM. The intra-address space cost is higher, but this is a limitation of the hardware. So this is on real hardware, the Sci-5 Unleashed, Hi-5 Unleashed from Sci-5. And this is one of the earliest hardware on RISC-V you could get, and it didn't have support for address space IDs. With address space IDs supported, that lower number should be the same as the upper number. So this is basically what we really expect in performance. And I said there's still scope for optimization. So this is cool. It basically means, yes, we have a performant kernel. We also have hypervisor support. The RISC-V hypervisor extensions, the virtualization support part in the privileged architecture spec is still in draft, and it's likely to go into certification process at the end of this year, so it will stay draft for a while. We've basically following the draft as it's developed, in particular as soon as it's supported by QEMU, and we have the maintainer here, thank you very much. And so we're following the spec as it evolves, and so far this has been all fairly straightforward. What do we do with verification? So this is the thing where HENSOLDT Cyber funding was critical, so they're funding this work, which is quite pricey, and it's all open source. It's all GPL'd, not just the kernel, but the proofs itself. So the critical thing, this is where most of the work goes, is this refinement proof from the abstract spec down to the C code. And I was really hoping to be able to announce today that it's done, but unfortunately, as these things go, it's not yet. So we're probably a month or two away from having this done, but it will be happening this year. Otherwise, we're in deep shit. Sorry, I'm not supposed to use terms like that here. We always deliver. And the tool chain for verifying that the binaries are correct, that the compiler didn't trick us, basically, is also target date for here is April. So that's very soon as well. And then we have RISC-V 64-bit verified. We're also working on the sound, on the worst case execution time analysis, but that's unfunded, and therefore we haven't committed to any particular dates for that, but it's in progress. So this is cool. We're a couple of months away from having the open source seL4 kernel completely verified on the open RISC-V ISA. What did we learn here? So we have RISC-V has multiple processor modes, the S mode where the kernel runs, and the U mode where applications run. It's pretty straightforward. What we learned here is actually not all that much, because it's a pretty straightforward architecture. The only thing to learn is, okay, it's a simple and clean architecture, therefore porting the kernel was pretty straightforward. The first prototype was done in a couple of weeks. And verification in general was also not particularly difficult. It's not yet finished, but all the hard bits are done. And yeah, it's clean architecture always helps, basically. There are a few things where the cleanliness or the simpliness was created a bit of extra work, particularly with page tables. Verifying usage of page tables is actually one of the hardest parts in the kernel verification, but we got on top of that. The hypervisor support is even simpler. So hypervisor support in RISC-V works this way, that it's a bit like x86 almost, in a sense. There's sort of an orthogonal mode. It's not quite a separate mode. It's basically, there's a version of supervisor mode where you have access to additional registers for the virtual machine state. And then there's a corresponding user mode, and this is where we run our virtual memory machine monitor, the actual thing that does emulation, etc. All very straightforward. The model is very simple. What RISC-V also has is so-called M mode for machine mode, and this is meant for the firmware. It's initially when the machine boots up, this is the only thing that has control over anything privileged in the system, and the typical thing is it then delegates stuff up to S mode. And the way we run it is we keep this M mode as simple as possible, really just consider it part of the hardware initialization sequence, delegate all the privileged state handling up to the microkernel running in S mode. But of course, it's security critical, so eventually we'll have to verify that. What M-mode also does is it allows you to easily emulate things that are not implemented in the hardware. For example, we have a processor without hardware ACID support, so we just can emulate it in the firmware. Basically, when you touch the ACID register, it does a flush and flush of the TLP, and then you go on. The nice thing about this is unlike Intel, where you have like 3 or 4 more privileged modes under the most privileged software accessible mode, and you have no idea what's going on there, and you know there's actually bad things going on there, etc. This is so clean and nice, and you know exactly what modes are there, and if you either have the code or not, but if you have it, then you know what's going on. The one concern with RISC-V is because it's this open architecture, where people are doing extensions, etc., there is a risk of fragmentation, that the ISAs fragment and you have portability issues. The community is quite aware of that and trying to manage that risk carefully. But the jury is still out on that one. And the other thing is they have just blessed a formalization of the ISA, and it's a really good formalization in the sense that the logic, the formal methods framework used for this formalization is very readable, and our engineers actually like it. They like to read this to find out how the hardware is exactly, how the hardware is supposed to operate. So it's much better than these informal descriptions you have for other architectures. And of course, eventually all the conformance testing will be based on that ISA formalization, and eventually people will actually verify processor implementations, the VHDL descriptions, etc., against this spec. So there's lots of potential, and I'm really excited about RISC-V because it's a game changer, and it will enable a lot of things, and you can already see all the innovation is moving out of x86 and ARM into the RISC-V space, which will put a lot of pressure on the other processor manufacturers. Okay, now a quick detour away from RISC-V. Anyone here attended my talk 2 years ago at LCA? A few people did, okay. So there I talked about what we call the mixed criticality support. I mentioned it earlier. And it's basically a more disciplined way of managing time. So in the classical seL4 kernel, we have very simple approach to scheduling. We have a priority and time slice with every thread. And we generalize this time slice by replacing it with what's called a scheduling context capability. So that's a capability in the sense of prima facie evidence of access. It points to an object which is a scheduling context object, and that defines the properties. It basically defines what access to the CPU a thread has. So it gives a period and a budget, and the constraint is the budget has to be less than a period, and the kernel guarantees you that in any time window that's no bigger than the period, you cannot consume any more time than the budget. So it's a very strict way of limiting CPU bandwidth access. And it's an enabler for, so this is examples of budgets. You can have like the left one gives you 2/3 of the access of the CPU bandwidth at a fairly narrow, fine-grained time scale. The right one gives you 1/4 at a much higher time scale. And you can then reason about processes being able to meet their deadlines even if they're not the highest priority thing in the system. And this is the first time, together with concurrent work on a different system in the US, where capabilities have been used for authorizing access to time in a way that's suitable for hard real-time systems. So in my eyes, this has been I'm a bit biased because I was involved in this work. It was done by my brilliant student, Anna. But this is, in my eyes, the biggest step forward in theory of at least microkernels, if not operating systems in general. Okay, so this thing is now also in verification, also pretty close. So what we have here is mainline ARMv7, which is where we have the full story. Then we have RISC-V, the same mainline kernel, the RISC-V port, where I said we're a couple months away from finishing the formal correctness proof, and then the tool chain roughly in April, the binary verification tool chain. And then at the same time, we're verifying this mixed criticality support kernel, which is a different branch of the kernel. So our verifiers pretty much have their hands full at the moment, working, basically verifying 2 different kernels at the same time. And this is also meant to be finished within a month or so. Chances are this will probably be a bit earlier than that one. And then when they are finished, then we're going to merge these 2, and we have the new mixed criticality kernel verified for RISC-V. And then we have our main architectures verified with the new kernel model, and then we can get rid of the old model, and the mixed criticality kernel will be the new mainline. So there's going to be a major change happening in the mainline kernel. It's actually in the process of happening. Things get merged as we evolve and verify them. So this is pretty exciting from our point of view, in the sense that we now have not only a kernel that's verified for really strict security, but also we have then a similar strict story for safety of real-time systems. For things like aircraft, autonomous cars, etc. Awesome. Yep?
One question. Is there a lot of dependency for the mixed criticality part on the architecture?
No, it's essentially orthogonal. This is why we expect the merge to be pretty straightforward.
Okay. So basically verifying ARM7, putting in the port for RISC-V, you just rerun the verification.
It's not quite that. There's a few changes that affect the things that are in the legacy kernel and the architecture dependent bit, but it should, the estimate is this merge will take 2 weeks. Okay, so I mentioned timing channels before. At the moment, this is something no operating system has any recipe against. There's no systematic defense against timing channel, and we want to change that. So obviously 2 years ago, Spectre and Meltdown hit the news. It happened while I was bushwalking in the Atacama Desert and came out and the world had changed. And what's behind that is speculation. We all know that, right? Spectre is about being able to use previously unidentified or unthought through side effects of speculation to reveal secret information. But the speculation bug or feature, no matter what you want to call it, alone is not enough. It needs a timing channel, a covert channel to pull the information out. So it's only the 2 that actually make a successful attack. And there's an interesting lesson there. So the speculation implications were what I call an unknown, because except for a few people suspecting that there was a real problem, and the people who worked on the Spectre paper, they worked on it for years, literally. Other than those, no one had any clue about this being a security hole. In contrast to these microarchitectural timing channels, they have been known for decades, and the community choose to ignore them. Who cares about timing channels, right? And in a way, we got what we deserved, because we ignored a problem that had security implications for decades. And well, it's frustrating, because I was actually trying to publish work on defeating timing channels for a while, and no one cared, because, oh, why would you want to care? Well, the world changed. Suddenly people are interested in that. So what's underlying these so-called microarchitectural timing channels, so these are cache channels, etc., is shared access of hardware resources. So there's 2 different protection domains. For simplicity, I call them high and low. And they share hardware resources. And because they're shared hardware resources, one part using it affects the execution speed of the other. And that's what creates those channels. So it's inter-process interference through microarchitectural features. And the point, what makes them tricky to deal with, is these features are hidden by the ISA. And the ISA, that's our hardware-software contract, right? This is what operating system people and architects agree as their interface. And notionally, if both sides stick to it, you should be able to build a correct system. The problem with the ISA as the hardware-software contract is that it's purely functional. It allows you to build functionally correct systems, but as we know now, it's not sufficient to guarantee that you can build secure systems. So that's the main problem here. And so how do you get around it? Basically, okay, so you have caches and their footprints and the caches overlap, etc. And this is what causes the problem. And the conclusion to that is the only way, principal way to stop this is you have to prevent the undisciplined sharing. So basically you have to partition those resources, and you can partition them either spatially or temporally. And temporally, of course, means secure multiplexing. And this is what we call time protection. Time protection means the operating system carefully partitions either temporally or spatially all the shared resources to prevent timing channels. So spatial partition means you can apply that to caches, where you make sure that by cache coloring, which I'll explain in a second, your footprints don't overlap, and then there cannot be any influence of the one execution on the other. You can't do this for everything, because, at least at the operating system level, because anything that's on core is addressed by virtual addresses, and virtual addresses are not under operating system control, and therefore the operating system can't do anything for partitioning those. And in general, it wouldn't make sense anyway for performance reasons, but that's a different one. So you need temporal partitioning, which means safe multiplexing, which means resetting the state when you hand it over to the other domain, and that's typically done by flushing. And that also has its limitation, because if there's concurrent access, if you have a shared cache, two cores access it concurrently, you can flush everything you want. You still have the interference because of the access being concurrent. Flushing only helps if the accesses are sequentialized. Okay, so bottom line is you need both. And so how do you do the spatial partitioning on caches? That's based on the way the associative lookup of caches works. Because of that, certain pages of memory or memory frames can only be cached in a particular subsection of the cache. And by allocate these so-called colors disjointly to processes, you can guarantee they cannot interfere in the cache. So for any physical address caches from the L2 down, this works easy, not hard to do at all. The problem you have then is, okay, anything that can interfere, including kernel data, needs to be partitioned. Turns out in seL4 this is trivial, because we did this lazy approach of handing all the responsibility for memory management to user level, and this helps proving isolation. It means you have to BYO malloc library and a few other things. It provides also really great ways of shooting yourself in the foot. So this is why seL4 is not particularly easy system to use, but it has really powerful implications. So by partitioning user memory, because kernel metadata can only be allocated in memory that's explicitly provided by the user, partitioning at the user level extends into the kernel space. So we get partitioning of kernel data for free in seL4. Trying to do that in Linux would be a bit of a challenge. And then the thing we had to add is you still have the shared kernel image. That could also be used for a channel. And so we add the feature where we can clone new kernel images. And each partition now gets its own kernel image. That sounds a bit strange, but it's actually not particularly difficult to do. So when the red partition executes, the exception pointers point to the red kernel, the exception vectors, and the red kernel handles any system call. And then when the blue executes the other one, and you have to be a bit careful on the handover. A partition switch now means a switch of kernel image. That was interesting, not particularly hard to do, but it's a feature that you can do in seL4. It's actually, the overhead is minimal because the kernel is only 150 kilobytes or so, right? It's not like the megabytes and megabytes of the Linux kernel. Okay, and so how does the temporal partitioning work? This is a very abstract representation of a context switch user context, read, program, timer, and return. To remove any history dependence, we need to flush the on-course state. Problem with this one is that the latency of that operation depends, for example, on how much dirty data is in the data cache. So that could be used as a channel too. So we need to pad the flush time to its worst case. And then we still have an issue of a potential history dependence on the return instructions, depending on whether they are in a lower level of the cache, in the L2, for example, determines on how fast this return to user executes. And so to make that deterministic, we touch all the data we need to return from the kernel before we do the padding. And then we have a totally deterministic context switch. And so we implemented that, and it mostly works, but mostly is never good for security, right? So we scratched our heads and dig deeper and deeper, and what meant to be done in like half a year turned into a 2-year project because in the end we found the hardware is fundamentally broken. And that's independent of manufacturer. All the processes we looked at 5 or 6 in total, x86 and ARM processors. They all were broken from the security point of view in the sense that there was state which the operating system is unable to get rid of. And that state depends on execution history and therefore can be used as a timing channel. And most have to do with the branch predictor. So this is a high silicon A53. What we see here is a so-called channel matrix. What you need to look out for is there's an input signal. This is the state on the high side. And there is an output signal, which is the execution time of the attacker. And if the execution time of the attacker depends on the state on the high side, then you have a channel. So look for horizontal variations along horizontal lines in this graph, and you know you have a channel. And obviously, it's pretty strong here. This is a particular simple one because it's the branch history buffer, which is a single-bit channel. So there's only 2 possible high states, but you can see there's a very clear dependency. And there's no architected means to get rid of that state. x86 is slightly better, but only quantitatively. The channel is smaller, but they have the same channel in the history buffer. And they have very clear channels in the prefetcher. There's prefetcher state you can't get rid of, etc. So basically, existing hardware is broken. And the main message here is the problem is our hardware-software contract. The ISA is not enough to provide security. So we need to change the hardware-software contract, and we propose this augmented ISA or AISA, which basically is a contract that says any shared hardware resource, you need to give the operating system a way to temporarily or spatially partition it. Now, obviously, getting this past Intel is hopeless. I've been telling them that for years, but of course, why would they listen to me? That was before Spectre, by the way. And ARM, of course, they have to change. Intel can actually fix all of that in microcode. And they choose to do some partial fixes as a response to Spectre. It wasn't enough. With ARM, it's harder because it's all baked into hardware, right? RISC-V to rescue. This is back to the topic. The RISC-V community is actually jumping at this. And yes, we want to be the most secure architecture, and they are very supportive making it happen. Which gets me to the last topic, which is comments about ecosystem. First, the RISC-V ecosystem. What did we learn from our engagement there? So there's the RISC-V Foundation is structured into standing committees which have task groups under them. And anything to do with security is the realm of the Security Standing Committee. And they actually invited me on there to talk about seL4 in general, but then I used this as an opportunity to push the time protection story, and they were extremely receptive. There's people there, mostly from big manufacturers like Western Digital, who's a platinum sponsor here. They want to be able to say RISC-V is the world's most secure architecture. And so they're extremely supportive of all this. Anything to do with the ISA, of course, is under the supervision of the privilege spec technical committee. As it was then, it's now a standing committee. And they were a bit harder to engage with. Well, actually, it's not true. We provided feedback on hypervisor expansions. They were very easy to engage with, very positive, came back with very positive proposals for addressing the needs we had. The time protection was a bit slower to get traction, but I totally understand why, because they have to be skeptical with some academic coming away and say, you have to do this and that. It's a RISC architecture. You already want to make sure that you don't die of featureitis. In a way, it's the same as with microkernels. I take the same attitude with the seL4, right? The blocking of any feature requests. But we're not getting there. So the standing committee explicitly helped to get the attention of the RISC spec, and they're now on board, and we will see some proposals coming in the next few months. Final topic, which is the excitement of the day, is we're setting up the seL4 Foundation. So seL4 has been open source for 5.5 years, and we're now taking that to the next level. So we're setting up a foundation under the Linux Foundation with the aims of really, providing a neutral entity, and this is important. There's big companies basically making a bet on seL4, building their products on seL4. And they're really worried that, okay, seL4 is basically on the whim of Cyro. They could remove funding any day, etc. And I understand that totally, there's concern. And they want more stability, predictability. And that was one of the drivers. Generally, of course, the idea is to enhance build up the ecosystem and increase community participation, standardize the system, not just the kernel, and protect and promote the brand. So with seL4's verification story, there's a real risk. Someone hacks the kernel, builds in the system, says this runs verified seL4. They introduce the bug. Someone hacks it. Will be huge reputational damage. We know it's not verified. They hacked it, but it might be too late. So we need to be really careful about protecting the brand. Linux Foundation has the firepower to do that. And one of the most important things, there's a few big ticket items. For example, we want to verify the kernel on ARMv8. That's an order of $1 million cost. We want to do multi-core verified. We have a high-performance multi-core version. It's not verified. That's a few $1 million. A lot of people interested in that. It's basically above the pain limit of each of the individual organizations. This is the way to come together and pool these resources. So I'm fairly confident that in a year or so, we get some of these big ticket items funded through the foundation by basically people pooling together. The structure is, as I said, it's set up under the Linux Foundation, so this is their standard template. You have under the Linux Foundation the seL4 Foundation with its own board, a fund charter, and a directed fund. So this is where we collect the money to fund the development. And then there's the projects, LLC, so that's a company that's actually the legal entity behind all this. There's a virtual company then for the actual seL4 Foundation. This will own the trademark, the GitHub repo, the domain, etc. And then there's the technical projects where the actual community participation happens. And you have to be a member to have a say. In order to become member of the seL4 Foundation, you have to be a member of the Linux Foundation. So the membership fees here, I quote, in addition to what you have to spend to become member of the Linux Foundation. Associate members, these are for individuals or nonprofits, they're free. And then there's a technical steering committee, which has the technical contributors in there. And then there's a board, and the feedback from the initial stakeholders were they really wanted to see us keep control over it, so they wanted strong representation. That's why we have 3 directors, and then the others come from other members and the technical steering committee. And there's an initial board, and this is all on the website, which is live by now. And important thing, this is how we want to see the communicating engagement. So there's, at the bottom is the kernel and its proofs. Kernel is 10,000 lines, just a microkernel, its proofs. And this is where we need to keep control, because very few people have the insight of being able to suggest changes to the kernel that we know can pass through verification. We expect the community to provide platform support. And then above there, there's a core user land. This is all stuff that in Linux would be part of the kernel. We provide the initial ones. We hope the community to participate and adopt. And everything higher up, we basically show the way, and the community hopefully will take it on and run with it. And yeah, I was hoping to be announcing that it's open for members. We just got feedback from Linux overnight for the legal documents. There's another round of discussion needed, but we're literally days away from being able to sign up members. And there's a website. Thank you.